record in the other classes. So, and independent trials of the same chance process, and count the number of times a particular success occurs. I don't even know. It's just they're attached to PowerSchool. Yeah, no idea. I can't even find my own stuff usually. So this is the binomial setting. It simplifies a lot for us if the conditions are right. So we have some conditions. And the conditions must be checked. If you're doing a problem for me, for a test or something like that, you got to list them out. They don't have to be really long. You just have to show me that we met the conditions. The first condition is it binary? Binary. In a binary situation, we have two outcomes: success and failure, and that's it. No, it's going to become something else. So you either have success or failure. A good example of a binary situation is flipping a coin. You either get what you want or you don't. Michael?
Another example is the APUS safety test.
The what?
You should have taken it. You're a certified welder. It's the safety test. It's 100% or you fail.
You remember, I'm old enough to not have ever had to have safety anything when I was a kid, right? And when I was a young adult. We didn't do safety.
Yes, I
We just burned ourselves. Okay, shh, Michael. Enough. Okay. One outcome does not affect another. Is it independent? Yeah, flipping a coin would be independent, right? If you were doing it multiple times, each flip is independent of the others. The next one is number. And we're using some of these words because they fit the mnemonic, but there is a fixed number of trials, and that number is known in advance. There's a fixed number of trials. So I'm going to flip a coin 5 times. And I make that statement before I do it. If I flip it 5 times and then decide to flip it one more, I just broke the condition. Okay? And same probability. The probability of success is the same for each trial. So what do bins. I think it's kind of like SOHCAHTOA, except not as good.
Please never mention that name.
Okay. So, in the calculation, when we get to the calculation of this, we have the binary coefficient. Now, a coefficient is a number that multiplies something else. So, for instance, in a linear equation, m, the slope, is the coefficient of x. It multiplies. So the binary coefficient is a multiplier. It is the number of ways to arrange k successes among n trials. The number of ways to arrange k successes among n trials. I'll see if I can answer your question here in just a second. So imagine I put 5 chairs in front of the room, and I take 3 of you guys as students, and I try to figure out how many different ways can I arrange 3 students into the 5 chairs. That's what k success would be. It would be the 3 students being arranged into the chairs. So how many different ways could that happen? That's sort of where that's going. Yes?
In the 2 videos, on like the deck of cards,
Yep.
they did the 4 times 3 times 2 times 1, but then in the other video they just did 2 to the 10th power. How is that different or the same?
In the first video with the cards, it's because each card that you put in an arrangement now changes the number in the deck. So once you've arranged one card, say the first card, the first 50 of the 52 cards, then you only have 51 cards that you can, right? There's 51 spaces that the next card could go into. That's why that works that way.
And that wouldn't be a binomial setting because...
Well, hang on to that thought. Hang on to that thought. How this is written is this: n over k with parentheses. It looks like a fraction, and you'll probably see me make a mistake and write that as a fraction because it takes just about every bit of my effort not to put a line between those. But it's not a fraction. This is the binary coefficient, and how it calculates is this: n factorial over k factorial times n minus k factorial. And n factorial would be n times n minus 1 times n minus 2, and we keep going until we get down to 3 and then 2 and then 1, right? So 5 factorial would be 5 times 4 times 3 times 2 times 1.
That's the video.
That's
Second card.
exactly. That's the factorial part. It's called factorial. And you probably want to know that 0 factorial is 1. I understand there's a nice YouTube video of that. If I can find it, I will. But it's kind of like any number to the 0 power is 1. I imagine it's sort of related to that. So if we have 0 factorial, it's 1. Yes?
Would it be 2 then 1 because don't you go down, or is it 1 then 2?
So this is going to be n minus 1. Let's say n is 52.
Oh,
So this is going to be 50, 51,
yeah.
50,
So it is
right?
going down, but
All
it's
the way. And it keeps going until you get to 1. That's what this is trying to say. Yes?
Why is the N just over the K? I just asked it.
It's just how it's written. I can't answer that question because I didn't make the notation. It's just how it's written.
You can't just run those next book.
There's probably somebody that can explain it. It's not ever anything that I've felt the need to pursue an explanation on. Okay, it's probably because it's not a division problem. Not here anyway. It's not. So, all right. So we'll mess with that here in a second. But that's just part of the formula that I'm going to give you. Is everybody with me? Yeah. Okay. Now the binomial probability formula. This looks like, well, let's put some more detail in there. Suppose x is a binomial random variable. With n trials and probability p of success, on each trial, the probability of getting exactly k successes in n trials is the probability that x equals k equals the binary coefficient times the probability that that event occurs to the k power times 1 minus the probability that that event occurs, so that's the event that it doesn't occur, to the n minus k power. It's not as bad as it looks. Remember, this thing is this n factorial over k factorial times n minus k factorial. We'll come back to that in a minute. So let's put it to use.
The factorials are represented by the exclamation point is correct.
I'm sorry, the what?
Factorials are represented by the
Correct.
exclamation point is
Correct. Exactly. So this would all be that 5 times 4 times 3 or whatever the number is that n and k are. So example, a family has 5 children. Each child has a 1 in 4 probability of having type O blood. What is the probability exactly 3 children in this family have type O blood? It'd be the K. Yeah. for what it's worth, I don't know if this probability stands for all people. I think it's probably a genetic thing for this family. But maybe I'm wrong. So the probability, the problem is asking, what's the probability that x equals 3?
Oh. Hey, hello, Gracie. Good seeing you.
It's so good to see you too, Josh. How
Is
are
it,
you doing?
good, how are you? I saw your friend Kaylin yesterday.
Oh, that's so cool. Did you say hi to her too?
Yes. Well, good
All right.
seeing you, Gracie.
It's good to see you too.
I gotta get going now.
Okay, bye, Joshua.
Bye, Gracie.
Oh, wait, not that one. Not that one.
Oh.
You can't take that one
Why?
because it's not recyclables.
Oh, okay. And
These guys over there are. Thank you, though.
you're welcome.
All right. I've lost some important stuff in the past to over enthusiastic recycling. All right, that was a special treat. Okay, so here's how we would write this. The probability is 0.25 or 1/4. I'm going to raise that to the third power. Whether you put the exponent in or outside of the parentheses in this case doesn't matter.
Not putting the line between it's
I know. I'm telling you, it's every time I draw it, I want to put a line there. Now, if I write this out a little bit simpler, this is going to be 5 factorial divided by 3 factorial times 5 minus 3 factorial times 0.25 to the third power times 0.75 to the second power. Let's see if we can get this done in the calculator.
how do we add the factorial?
I'll show you in just a second. Let's talk about these factorials real quick, though, because sometimes they're quicker to do in your head than they are to try to plug into the calculator. 3 factorial is going to be 3 times 2 times 1. How much is that? 6, right? And 5 minus 3 is going to be 2 factorial. So what's 2 factorial? Actually, this factorial should be on the outside here. I wrote that wrong. 2 times 1, it's just 2. So this is just 6, and this is just 2.
5 factorial 5.
So here's how we're going to put this into the calculator. We've got to find factorial here. So I'm going to go 5.
Wait, how much is each factorial?
I'm not sure I understand your question. Let's get to factorial here first. Michael, let me see if by doing it the question is answered. So if you go to math and you go over to probability, you should find factorial pretty easily. Excuse me. I don't know of a shortcut on that. I wish I did. So 5 factorial, and I'm going to divide that by, well, this is 6 and this is 2, so I'm going to go 6 times 2, but I'm going to put those in parentheses, otherwise it's going to be a mess. And I'm going to go ahead and hit equals at that point and get, I got 10. So this whole thing is just 10. Now I've got to multiply that times 0.25 to the third power times 0.75 to the second power. You guys find that all right? Everybody get the factorial in there okay? Okay. If you don't put parentheses around this, you get a wrong answer. It's like 40 or something like that. Yeah, you got to put the parentheses around it.
Raised to the third power.
Yeah, 0.25 to the third power times 0.75 to the second power. And you should get that it's about 9%. There's about a 9% probability that exactly 3 kids will have type O blood in this family.
8%.
Yeah, it's like 8.7, right? Almost 8.8, yeah. It's pretty close to 9%. Now, this thing right here has a shortcut. Let me show you the shortcut. If you go back to math, does anybody have one of the older calculators? put in 5 first. If you have one of the older calculators, put in 5. If you have one of the new ones, just go to math. Go back over to probability. And you want NCR. What this really is NCK in our context. And you put the 5 in before the C and the 3 in after the C. Because we're picking 3. How many ways can we get 3 out of the 5 that have the type O blood? And then hit enter. Did you get 10? You should get 10. That's the same as that. It's the same as doing this guy right here. So this thing up here equals NCR, where R is K in this context. This is combinations. How many ways can I arrange 3 people into 5 chairs? That's a way of expressing what this is telling us. And this is saying there's 10 ways to do that. All right. Now you want the super shortcut? See, here's the thing. If I give you the super duper shortcut from the very beginning, we'd have been done with this conversation 30, 35 minutes ago. I would have felt like all I had to do is sit down and read the newspaper. But that's not me. So it's more important that I show you how miserable life could be if you didn't have the calculator, right? So it gives you an appreciation for the technology that you have. Binom PDF. Let's do this problem with a shortcut, and we'll talk about what that is. If you go second and then vars, go into your distribution, second vars. Now binom PDF is going to be way down at the bottom, so it's easiest to go up to get to it. Find binom PDF. It's A and mine. I think it's probably the same for everybody. Go ahead and click on that. Trials, in this case, that's how many kids are in the family? 5. Probability? 0.25. Oops, wait a minute, I goofed up.
Is it 0.25 because it's 1/4?
Because it's 1/4, right? And the x value, how many are we looking for? Exactly 3. We should get the same here as here. Yeah, I thought PDF was a file format.
I know, that's what I
Digital file.
Okay, PDF. What I want you to know about PDF, or how to remember it, is precisely equal to.
I'm not finding the function here.
Okay, then try to follow this one. There's another one, binom CDF. So let's try binom CDF with the same problem. And then we'll see what probability that gives us, and I'll talk about what that is.
Where did the 3 come from again?
The 3 is how many we want to know. What's the probability exactly 3 have type O blood? Yep. Out of the 5, what's the probability 3 do? Okay, so if we go back to second vars, find binom CDF, choose that. It's going to ask you the same thing. How many trials? 5 kids. I'd love to think of my children as trials. That would be awesome.
I think you already do.
0.25, yeah, but I only have 2, so I only have 2 trials. It's not very exciting. X value, 3. Paste. 0.98. Now that's a pretty different thing. So here's what the CDF is. CDF, I want you to think of as in terms of up to that number. Precisely equal to and up to that number. So by doing the binom CDF, what we've done is we've calculated what's the probability that exactly 0 kids have probability that exactly one kid has type O blood, plus 2 kids have type O blood, plus 3 kids have type O blood. So this would be, what's the probability that up to 3 children have type O blood? About a 98% chance. So what's the probability of 4 or 5?
Probably closer to one.
Well, wouldn't it be, what's the probability that 4 or 5 kids have type O blood? Wouldn't it be 1 minus this? And you're right. If you just do the binom CDF and you change that to 4 or 5, it's going to get closer to 1. Yeah. Keep in mind, 0 is an option. The probability that 0 kids have type O blood is calculated in here.
But wouldn't it be like less of a chance that all of them would have it? Or is it?
It
would it
is.
get further?
What you're thinking of is the inverse of this. What's the probability that that you'd have 5 would be 1 minus the probability that you 0, 1 through 4 have it. So it'd be really unlikely that 5 would have it.
Oh, gotcha.
Right? Does that make sense? So it's pretty likely that at least that 0, 1, 2, 3, or 4 have it. It's really unlikely that all 5 have it. That's kind of what this is saying. This is,
There's a 99% chance.
Is that
it's almost.
or don't have it? Like,
So what it's, okay.
I read that.
What this is saying is that there's a 99.9% chance that 0 have type O blood, or 1 have type O blood, or 2 have type O blood, or 3 or 4 have type O blood. Right? So any of those are an option. The probability that all 5 have type O
It's like
blood
point-
would be 1 minus this,
Yes,
which is
exactly.
almost 0. Right?
Yes.
Okay? All right.
Thank you, Mr. Mayor.
You're welcome. One thing I forgot here, real quick. The conditions. Did we meet our conditions? Is it binomial? Yes. Success or failure? Yes. Do we have a fixed probability?
Yes.
Yes. What else am I looking for? Would each child be independent? And do we have a fixed number of trials?
Yes.
Binomial. Okay. So give these problems a try.